All right, so this is Math 331, Lecture 31. We are in the home stretch. Plan for today is to talk about some harmonic problems. There's going to be a presentation by someone in the class on Wednesday, I believe. They're just making sure the code works on some things related to the egg drop problem. One generalization of this, if you want to think about it, is a two-dimensional version of egg drop. So what if you now have a rectangular grid, and you know that if you drop an egg from a point and it cracks in anything to the up and right. And let's say you know that there is some special point such that the region that's cracks is something like this. So you could potentially have had a shape like this, but let's say you know the shape is like this. How would you find the most efficiently as possible where to drop the eggs to minimize worst case scenario in a two-dimensional problem like this? And then of course if you can do two-dimensional, you can do three-dimensional, you could do also strange shapes. Whenever you see something in mathematics, the goal is always, interesting, can I tweak this? Can I ask something new? Because there's a lot of problems like this that are out there that people have not looked at other than just what's being done. And a large number of my papers, a lot of my successful papers, have come from taking things that have been done and trying to ask other questions. This is one of the reasons why when I go back and forth, was my physics degree worth it? I think so because it has me asking different questions than I would have if I had just taken math classes. When I see lectures that are very heavy in algebraic topology, I don't quite feel that way. But overall, being able to ask a good question, that's 95% of research. A lot of it is then trained monkey work. Did I tell you about the potential lawsuit that could have been filed against me on my Fibonacci paper on Benford's law? So when I was a graduate student or postdoc at Princeton, I made some notes on how the Fibonacci numbers satisfy Benford's law. About 30% of the leading digits are 1. It was just very natural to just write this up for what I was doing with my class. And then a little bit later I searched the literature and I found a paper in the Fibonacci Quarterly which has almost exactly the same string of numbers in almost exactly the same order. And the reason is, as soon as you think to ask the question, this is how you go about it. Now of course the danger is there's been a lot of great mathematicians before you. Have you heard of the phrase anticipatory plagiarism? This is when Gauss has your great idea 200 years before you're born and steals it. And so the problem is a lot of things have already been done. And you have to be aware of what's in the literature. You have to spend the time searching. But when you're searching, when you're reading things, always ask, how can I push this further? All right, I guess as long as we're here for another thing pushing it further, we've talked about a couple of variants of tic-tac-toe. We all agree regular tic-tac-toe is boring, right? There's three-dimensional tic-tac-toe, where you have one board on top of another on top of another. And if you're trying to play 3 in a row, it's still boring. Especially because the first person now has a winning strategy. Have you guys heard of ultimate tic-tac-toe? I will just mention ultimate tic-tac-toe and then we'll get to the main thing of the game. So the way ultimate tic-tac-toe works is you have 9 tic-tac-toe boards. And so I played weak ultimate with my kids yesterday as we were going out for dinner to celebrate the Red Sox finally scoring a good number of runs on offense. Okay? So there's 9 boards. Somebody choose a board and choose a spot on the board. Center. You've moved in the center board. I now have to move in the center board, but I can move anywhere I want. So I'll move upper right corner. You now have to play on the upper right board. So your board is now determined. So where do you want to go on the upper right board? You don't have to play optimally. We're not playing against Swarthmore. Swarthmore's not playing against us. Just something for quickly. So if you choose the center to take the center of this board, then you allow me to come back over here. So you took too long, so I'm going to give you the center, and I'll come back here. All right. Now, where do I want to go? Maybe I'll go over here, and that'll force you onto this board. So the way I played with my kids is first one to get 3 in a row anywhere wins. The way ultimate tic-tac-toe is truly played is if you get 3 in a row, you win that piece, and then that piece becomes yours. So let's say you have to go up here, and you again stupidly choose the center. I will go over here, and now this whole board becomes a giant O for me. Then there's a couple of variants you have to put in. What if all the squares in a board are filled? The standard one is then the next person gets to choose any board they want to go to. What if a board ends in a tie? Either no one gets the square or you can count it for both X and O. So you have to figure out how you want to do stuff like this. But this is a really nice variant of tic-tac-toe that makes the game interesting again. I believe player one has a winning strategy, but it might be an involved enough strategy that it's not a huge deal.
What happens if you're in like the top corner and you go to the top corner?
So I would... So this is, again, you would have a choice. So for instance, there are still squares available in this board. Would you say that the board is unavailable now? Or would you say you have to go in one of the other places? And then you can make a new game. And this is exactly what you should be doing, is looking at generalizations. What if this board is originally an O board, but now you end up getting a couple of X's from things they don't? Now it could become both an O and an X board, because we both have 3 in a row there. And then potentially maybe I get O's again. Well, now it's O's twice and X is only once, so it's going to count as an O board because its net excess is O. So you can absolutely put in tweaks like this, and depending on the tweaks you put in, you will have different answers for what the optimal strategy is and maybe whether or not a player has a winning strategy. So all these things often come down to, does someone have a winning strategy? I may on Wednesday or Friday go through a game where you can prove someone has a winning strategy without having any idea what the winning strategy is. It's a fun game to think about, where I can prove to you that you can win if you go first, but have no idea how you would find those winning moves. Okay. Since this is a 300 level college class, we should be doing things a little bit more involved than tic-tac-toes. Then kind of feels foolish to then go back to dominoes, but all right. So the question is, we want to figure out what is the optimal way to stack dominoes. We will assume all the dominoes have uniform density, and it's the same density. This is not quite right. If you look at this, they both have 6s here. This has 1 dot, this has 2 dots. Maybe this one is a little bit lighter than this one because a little bit more has been cut out. And maybe the density is not quite uniform across it. Would this make a difference? It might require me to slightly shift things a little bit to increase stability. So we will assume these are idealized dominoes. Right? Are we doing this in a vacuum or are we doing this in a planet with gravity? Yeah, because if there was no gravity, just put it on ever so slightly, just a little bit over like this, right? And just keep stacking because nothing will pull it down. So we've got to assume that there's gravity. We can make the assumption that the gravitational field is constant. We're not going to have to worry about the small incremental height. Although since we can't go off to infinity, well, maybe if we are doing a giant domino tower, all right. But we will assume an idealized, constant gravity. So the question is, what is the best way to be putting these dominoes to get the maximum overhang possible? And the idea is you need to keep it stable. And so a lot of you have come up with fairly similar things. Most people, when they do this problem, do it roughly like this. And then, so the next one will definitely crash the way of doing it, so I'll stop here. This doesn't look like it's nearly done perfectly. The reason I want to talk about this is not because I care about stacking dominoes for maximum overhang, but because I care about making implicit assumptions. So how many of you, when you first saw this problem, thought that the dominoes had to be moving constantly in one direction? That you couldn't have the dominoes going back and forth? Just your first thought when you were stacking this. It's natural to just implicitly assume I have to be marching in one direction. I'm trying to stack. If I'm trying to stack, I want to keep moving. Because at any given moment in time, the best I can do is, let's add another domino in the direction I want to go. That's going to increase things. So this is a really good general principle. Local optimal leads to global optimal. Any computer scientists here? They might call this almost like the greedy algorithm in CS. at every moment in time, do what's best. And there's a lot of instances where the greedy algorithm does a really good job. It doesn't mean it's always going to be best, but it's a very easily implementable strategy. And for a lot of things that are extremely complicated, if you have a strategy that ballpark gives you a good answer and is easy to implement, is easy to code, it's worth considering. Especially since sometimes it does do what's best. So as an example of when it can be best is Zeckendorf decompositions. Did we talk about this when we did the Fibonacci numbers earlier? Every Fibonacci is a sum of non-adjacent Fibonaccis. And you can do this uniquely. And the way was the greedy algorithm. Take your number, remove the largest Fibonacci you could, look at what's left, remove the largest Fibonacci number you can. And so if we go n minus fi1 minus fi2, if these two were adjacent, we could have removed their sum, which contradicts this being the largest Fibonacci number we can remove. So the greedy algorithm will actually give you a decomposition here. There are generalizations, there are related sequences where the greedy algorithm no longer works. But for a large class of generalizations of the Fibonacci's, it will work. It's a good algorithm, this greedy algorithm. And it really is just doing at every moment in time what is locally best. Now, we did not do the dogs knowing calculus in this class, correct? So this will tie to some math we've seen before. Okay, it's kind of fun for the last week of class to try to tie things together. All right, so I have actually met this dog. His name is Elvis. I can't remember if he's still alive, but he actually did visit Williams. I've seen him multiple times. And he knows calculus. Or at least he acts as if he knows calculus. And so there's a nice series of papers on this. I will post them. So imagine Elvis is in the water, and you throw a stick right there. How does Elvis get to the stick? Come on, let's get some answers. How would Elvis get to the stick? What path would Elvis take? Straight line, right? I was going to just stop there, but given how hard this seems to be, if the stick is here, what does Elvis do? Wow, this is really tough, 9 a.m. What path does Elvis take? Straight line. The stick is over here. Stick is over here. Not necessarily. Elvis knows calculus. So we often make unreasonable assumptions, especially if we take economics classes. Let's make some reasonable assumptions about Elvis. What two parameters do you really need to know for Elvis in the water to be doing this? I don't know, I'm not sure if I said this is water. This is water, this is land. So what would we need to know for Elvis? What two key parameters matter for this problem? Yeah. Where do you think Elvis moves faster? On land. Unless Elvis has like 2 broken legs, Elvis will move faster on land than water. You know his speed on either land or water. What's his speed on either land or water? One of those 2 quantities you know, without loss of generality. Yeah, without loss of generality. Either his speed on water is 1 or his speed on land is 1. You get to choose, right? You can choose your units of measurement. One of my high school physics textbooks had the conversion factor between furlongs per fortnight and meters per second. I really can't think of that many instances where I need to know how many furlongs are being moved in a fortnight. But you can choose whatever units you want. Where would you want Elvis's speed to be 1, on land or in water? And you can make a good argument for either. I would probably choose water, because you could look at the situation where Elvis moves infinitely fast on land. If Elvis moves infinitely fast on land, you would want a path going straight down, over, and straight up. And that would work so long as the sum of those 2 lengths, say go to over here, is less than this connecting line. In general, since Elvis will not travel at an infinite speed, what Elvis will typically do is he'll come in at some angle, travel, and then come up. And then the question is, of course, what are these angles? Where does Elvis run down? This is very similar. How many of you have seen the drowning swimmer problem in calculus? So you have a lifeguard over here, and you have some swimmer who's drowning. Help. Or maybe we'll move them over here. And the lifeguard wants to take the optimal path. We will assume that there is no one on the beach, so they don't have to worry about someone being in their way. A lot of people think, well, the optimal path is run directly to them. The worst possible path, assuming we don't have a moron of a lifeguard, is to run straight towards land and then run at an angle. We'll assume the lifeguard is not going to spiral around, the lifeguard's not drunk or anything. Another good candidate path is to run directly underneath the swimmer. What is advantageous about that path? Minimizes distance in the water. This minimizes total distance. This maximizes distance in water. And in fact, it's the longest path. So this is clearly right out. The question is, where do we want to go? There's a trade-off. The further we go in this direction, the longer we have, the greater distance we have to cover. And it turns out there's a really nice quartic equation that governs this. The solution of this basically is Snell's law. Angle of incidence, angle of refraction from physics. What happens when you travel between two different media? It's very similar to what's going on. And so it's a really nice physics problem, has lots of applications in optics. It shows you how in very simple mathematics, good things emerge. I'm not going to go through the details here, but it is clear that as long as there is a faster speed on land than water, eventually the stick will be so far away that it's worth the time it takes to go to land. Right? What this means is there is a discontinuity in the trajectory of the dog as you move the stick. There's a bifurcation. It's going to be straight line, straight line, straight line, straight line, and then there's going to be a critical point where the dog is indifferent between the two routes. And then beyond that, in certain directions, it's actually faster to go on land. It turns out by analyzing this, you can prove one of our old friends, the arithmetic mean geometric mean inequality. So I often prove the geometric series formula by playing a game of hoops and shooting a basketball. You can prove the arithmetic mean geometric mean by looking at when these two paths are equal time. So I will post the article. It's a fun read that actually goes through the details of this. But what I like is it is another example where doing what is locally best does not lead to what is globally best. If you're the dog, at any moment in time, the best thing you can do is to swim straight to the stick. If all you care about is a split second later, I want to be as close to the stick as possible given that I'm starting here, you can't do better than swimming straight to the stick. But globally, you have this possibility of going down. And it's the same thing with the dominoes. Is that when you look at the dominoes, when we're stacking it like this, the best thing we can be thinking of doing is pushing it in that direction. Unfortunately for us, that's not the best solution. This is much easier to analyze. So one of the possibilities we can start to do is, probably building this on a weak box is not the greatest, but put a couple of things on top as like a giant weight. If I do something like that, that gives me a pretty good overhang. And then the question is just, how far should I be able to push these? How much weight do I really need? Do I really need to have 3 of them up here? No, but given how stable everything is, I think I'd rather do 3. I'll try removing one of them. Okay, it's still working with just 2. Nope, it'll definitely go off if I take off the 2. But okay, but that looks much better. And then there are other patterns you can do. And then you have to worry about how stable is it. So it turns out if you do the always to the left or always to the right, the overhang with n dominoes is about the nth harmonic number. So the harmonic sum is 1 plus 1/2 plus 1/3 plus 1/4 all the way up to 1 over n. It's about log n. If you are allowing yourselves to do forward backwards, you can get up to n to the 1/3. And I believe we've now shown that n to the 1/3 is optimal, that all that's remaining is the constant in front of n to the 1/3. So I think we have maybe like 0.2 n to the 1/3, and it can't be more than like 6 n to the 1/3, something like that. And again, this could be an order of magnitude, but we really don't care about something order of magnitude. Well, we care more about the power in n. And going from something that gives you a log n growth to an n to the 1/3 growth is phenomenal. And so one of the professors on the paper that's often cited was my first professor in college. So let's try to analyze the harmonic approach. So this is the dominoes in one direction. So the analysis is much easier here. But without any counterweights going in the other direction, we're going to have huge stability issues. And so the question is, how do you sniff out a formula? So I have deliberately not looked up how this is analyzed. This is the game of the class, is let's discuss things live. How should we do this? What approach would you want to use to figure out how to stack n dominoes optimally?
I guess you could just define some function that's like for each domino, you could look at the overhang of each domino,
Right.
and then you could just have the overhang be from the previous one below it.
Okay.
So then the total overhang is like the sum of them.
Okay.
And then to get you also have like a constraint, I guess, that if you look at this, the total center of mass.
Good. The center of mass has to be supported.
Yeah. And then it's
And actually, it's more than just the total center of mass. The center of mass at every point, from any point higher, must be supported.
Yeah.
And if the center of mass from every point upward is supported, we'll be fine. But so what kind of method of proof do you think we're going to use? What does this feel like? Which of our proof techniques? It feels a lot like induction, right? If we have a stack that's stable, then that means all the center of masses are okay. We just need to calculate the center mass of this whole thing and then place that down on the next one. And then just keep marching down. So it feels like an induction. It feels almost like a greedy. Do what's optimal at step n, and then for step n plus 1, take that optimal configuration and push it as far to the left or right of the domino as you can. So again, this is the point, is can you look at a problem like this and get a sense of how I should attack this? So let's try induction. One of the things that's wonderful about a subject like this is you get to choose your conventions and your notation. What would you say is the size of a domino? I'm sorry? Okay, that's a possibility. A domino is 1 unit. What's another possibility for the size of a domino? 2. And in fact, it's nice that this is cut with a little black line over here. This is why I bought these high quality dominoes from a yard sale many years ago. Is this a 1 unit or a 2 unit? When you flip coins for the central limit theorem, and you want to see, let's say if I toss a heads, I move left. No, heads is always right. If I toss a head, I move right. If I toss a tail, I move left. And I want to see where am I afterwards. This is like counting a head as a +1 and a tail as a -1. I could do a head as a 1 and a tail as a 0. But then I wouldn't have centered motion. So it's often nice to have a head +1, a tail -1, so that they balance. So when you think about something like this, when I put down the first domino on this, what's my overhang? In some sense, I'm going to have like factors of a half maybe. And so do I want to have a domino of length 2? Do I want to have a domino of length 1? In some sense, it doesn't really matter as long as you're aware of these factors. I think it makes more sense to talk about a unit domino. But maybe when we're doing the algebra in terms of trying to figure out where the center is, it might be better to have a domino of length 2. You should just be aware of these issues. You should be thinking of these issues. You have to make a choice, and it doesn't make a huge difference at the end of the day, but it can simplify some of the algebra. So we will use unit dominoes. Okay. Anybody want to tell me the optimal overhang with one domino? In some sense, I would almost say this problem makes no sense. The overhang is hanging above the table. If I have one domino, it's on the table. So sometimes when you do inductions, you have to be a little bit careful, where do you start? Or you could say, I'm given a domino and I'm building on top of that. And again, it's where do you want to start counting from? How many of you have seen the gamma function? So gamma of s is the integral from 0 to infinity of e to the minus x, x to the s minus 1 dx. And it turns out gamma of n plus 1 is n factorial if n is an integer. So the normalization is a little bit off from what you would want. This turns out to be a really good definition. You can view this quantity over here as x to the s dx over x. If you rescale x, dx over x is an invariant measure. If I rescale x by 12, dx over x is unchanged. This is a really good definition. It sadly doesn't quite match the factorial. And so you have to decide, which do you want? So when we're counting, do we want to talk about, where do we put the first domino? Is this the first domino, or is this the base domino that we build upon? And depending on what you choose, your formulas could be shifted by 1 from what's in the book. And that's another point to get from this, is always check the notation, always check the conventions. I will not mention the person's name, but when I was a postdoc at Ohio State, one of the graduate students who was working in the same area as mathematics as I did showed me his thesis, and you're very proud of the work he did. Okay, very nice. Do you know half your thesis is wrong? And his jaw just drops. And the reason was he was using a really nice paper, and that paper said all the results below assume that k is congruent to 0 mod 4. There's a trivial tweak if k is equal to 2 mod 4. And so he was doing things for even k, and he has to include a minus sign when k was 2 mod 4. It took less than 5 minutes to fix his thesis, and I admit I had probably too much fun with him, and this is one of the reasons why I'm wearing the Ohio State shirt today, to remember to tell the story. But for a few moments he was just in complete shock. And this was to really drive home the point that when you're reading a paper, you need to be damn sure you understand what is being assumed. This is why when I write papers and my students write papers with me, you have to state all the assumptions in a theorem. I don't like putting somewhere in the paper, henceforth we assume. It makes it a little bit more cumbersome to repeat this in the theorems, but it's good to do that. People do sometimes theorem shop. And they just look, oh, can I find this somewhere? You want to be clear, you want to know what's going on. So be very careful when you're looking and comparing formulas. We might be off by 1 number. Well, in the limit, being off by 1 domino is not going to make a difference, especially since it's going logarithmically. But it's good to be aware of this. This is just lessons in life. Okay? So do we want to call this the first domino, or do we want to call this the start? I think I know what I would choose. I'm just curious what you would choose. Would you choose to count this or not count this? Or is this the 0th domino? Any thoughts? So you would count this as the first domino, and the first domino has an overhang of 0.
Well, no, I would count it with the overhang.
With no overhang?
With overhang.
Well, what's the overhang? Nothing is hanging. It's flat with the table. So if we want to try to show like the overhang with n dominoes is the nth harmonic number, if we count this, I think, as a domino, we're going to be shifted by 1. So I think we want to count this as the 0th domino. So I would count this as the 0th domino. You know, again, it's not going to make a huge difference, but it really is worth thinking about how you want to label things. And at the end of the day, you want a nice, clean formula. So we will count this as the 0th domino. Okay, so then we'll really do for the base case. So here's domino 0. We now have domino 1. And we want to have the maximum overhang possible. And so we need the center of mass of the first domino to be over the 0th domino, or it will shatter. It will fall down. So, you know, clearly at this point the center of mass is over. The center of mass is going to be halfway. If I put this on exactly at the halfway point, it will just perfectly balance. So what we would do so this would be half a unit, and this would be half a unit. And so now we get the overhang is 1/2. And this is why you can see we might want to use dominoes of size 2. Because if we use dominoes of size 2, we double all the overhangs. And so now we're going to get a overhang that's half the nth harmonic number. So this is a it's not a full democracy, but it's a somewhat benevolent dictatorship that will listen to the people. If you want at this point in time to change the length of our dominoes to 2, I am willing to do that. If you want to keep them at 1, I'm happy to do that. What do you think? Should we change the dominoes to have length 2? All right? So let's... Now the overhang is 1. What's really nice about this is now we've doubled the overhang. Really bad joke. Right? We have not doubled the overhang by changing our units. Okay. You always want to look at your overhang per size of domino. And so you would just have to remember at the end of the day, no, we're actually not doing twice as well as anybody else using the stacking to the right method. All right. Should we go straight to the general case of induction, or should we look at maybe another case or two to build up intuition? Let's build intuition, right? For problems like this, it's not so bad. So now we have something like this. Okay. So this is, you know, n equals 1. Let's do n equals 2. Not to scale. The first thing we need to do is we need to make sure that the center of mass of this is over this one. And by induction, where would we want to put this? So we have 3 dominoes now, and by induction, we know where we should put that top domino over the second one. Where should we put it by induction? Half, right? That's what we've done before, right? It's halfway over. So we should do it halfway over. We have no choice if we're doing it by induction. So I should redraw this a little bit, and if this is about the halfway point, it should be something like this. So this would be 1 unit over here. Now we have to decide, where do we want to put this one over here? So how would we figure out where the center of mass of this is? Oh, they've removed the clock. The clock is down there. Great.
Center of mass should be halfway on the overlap, right? Of the top 2.
Well, for this one, Can we assume all of this mass is concentrated right here at this halfway point?
If you're just looking at where the top domino is on top of the second domino.
Right.
Yeah.
This over here is the halfway point.
Yeah, so would the center of mass be between, like...
Oh, so what you're saying is we need to find the center of mass of these two.
Yeah.
So the center of mass of this one would be right here. The center of mass of this one would be right here. So then it should be halfway between them right here. Then we can essentially assume all of this mass is concentrated at this one point here, all of this mass is concentrated right here, and just take the average of the two. Okay, if that's the case, then we now have we have to decide how much we want to shift things over.
Well, we use the same rule that the center of mass has to be...
The center of mass has to be, so we want the center of mass to be right over here. So this is going to be 3/4 of the way down this piece. So we want 3/4 of this piece to be right here. So this should be 1/4. And now you can begin to see, do we want to do it as a block of length 2 or a block of length 1? Do you want to switch back? What do you think? This is a little bit like the 2-envelope problem in probability. You have 2 envelopes. They're sealed. One has twice as much money as the other. If you calculate the expected value, you should switch. But then when you calculate the expected value, you should switch again, and you keep going. And the paradox in this is that you can't put a uniform distribution on the positive reals. You can't have both situations being equally likely. There's only finitely many dollars I can put in the envelope. But over here now, do you want to switch back and have the domino now of length 1 instead of length 2? So we will switch back. Overhang has now been decreased by a factor of 2 to 1/2. And again, sometimes you really do not know which you want to use until you actually get your hands dirty and do the calculation. You know, what's going to be the easier notation? All right, so over here now, we have something of length 1 on the bottom. Here is, at a plus 1/2. The center of mass here is going to be at 3/4. So we have some shift over here, x. So x plus, well, we've got to decide how we want to do this. Maybe we should call this shift here x. So just how do we want to set the equation? This amount over here, so so it's where do we want the unit? So here's the center, and here's the center over here. So it's how much do we want to move this over? So there's some amount that we move over. So it's just how do we want to do the algebra? There's lots of different choices. I could have this is my amount of moving. I could have this. I could have distance from the center. Where do I want to put my coordinate system? Do I want to put 0 at the center here? Do I want to put 0 over here? And then this would be at 1. So what's the best coordinate system? There's lots of choices. The center is an obvious choice. But I think also the lower left is an obvious choice for 0. And then we need the center of mass to be exactly at 1. That seems like nice units. Again, I'm not sure that this is the best. I have deliberately not thought about this problem. What do you think? Do you like that as notation? And now our variable could be maybe how much we shift over here. And then this place over here is going to be 3/4 the length. So this distance here is now 3/4. So we need x plus 3/4 equals 1. So x equals 1/4. How should we write 1/4? How should we write 1/2? Yes, we should write this as 1/2 times 1. How should we write 1/4? 1/2 times 1/2. Right? The whole point is that it's not always clear how you should view a number. Right? I would really view 1/4 as 1/2 times 1/2. What do we think the next number should be? Probably 1/2 times 1/3. Okay, and so now we would do, I don't know about you, but I know for myself, I do not feel like I have done enough of this problem to truly grok what's going on, and I think doing n equals 3 would be helpful. Okay, given that there doesn't seem to be a mass of people swarming towards me saying, no, 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 it's clear, let's do another one. So, but what I like is, it's not clear how to set up the algebra. It's clear what to do, but it's not clear what's going to lead to the most tractable thing. When you're doing problems like this, you have to have the willingness to try several different approaches. Sometimes take 2 or 3 different pieces of paper. Go with something for a while, and if it doesn't work, pause, put it off to the side, take a new piece of paper, and try something else. So here we'll have 0 and 1, and now we need to put the other pieces down. So now we have to put down 3 dominoes. And again, not to scale, which is a little bit unfortunate. So we know this distance here is 1/2 of 1, right? And this distance here is 1/2 of 1/2. And we're conjecturing that this distance here is 1/2 of 1/3. So by induction, we know the center of mass of this over this is going to be fine. And we know the center of mass of these two over this is going to be fine. So now we have to figure out what is the center of mass of this configuration of 3 things. So one thing is, we could write down, the coordinates of the centers and just take the average of them. So if we just looked at these 3, could we figure out where the center of mass is of those 3? And then we would just have to shift it over by however much this x is.
Can we assume by induction that the center of mass of the top 2 pieces are at...
Well, the top 2 pieces, because we keep just putting the next block shifting over to the left. So we will definitely have these 2 aligned so that the center of mass of these is at the 3/4 mark.
Yeah, so can we assume that the center of mass of the top 2 pieces is at the endpoint of the 3rd piece?
Oh, is that the endpoint of the 3rd piece? Yes, because that's the maximum thing we can do. Excellent. Yeah, that'll greatly simplify the algebra. Make sure you email me. Yeah, so we can assume that we have essentially two masses at here and then 1 mass there. And we knew this distance here was 1/4. Because this was at the halfway point, this was at the 3/4 point of the bar. So it's like we have a mass at 1/2 and then 2 masses at 3/4 and divide by 3. So I think that should be the center of mass. We have 1 piece at the halfway point and 2 pieces at the 3/4 point. So this would become 2 plus, actually I don't have to, because the 2 is going to cancel. It's going to be 1 plus 3 over 12 over 6. Right? So we get that the center of mass of these 3 pieces is at 2/3. Does it make sense that it's not as far as the 3/4?
setting the coordinate system.
So right now I'm saying this is 2/3 of the distance from the end of this third piece. Right? Just if we look at this third piece, the center of mass is going to be 2/3 of the distance from here. Because I've got one piece that's halfway and two pieces that are 3/4 of the way. And so it makes sense that it shouldn't be as far because I'm pulling it back a little bit. So we'll see in a moment if this makes sense. So this would be 2/3. So if this is x, we would need x plus 2/3 to equal 1. So it looks like we're off by a factor of 2.
Well, I think if we're considering the distance from the corner of the third piece, then it should be 2 times 1 instead of 2 times 3/4, right? Because the top two pieces have their center, a total center of mass at the other end point of the third piece.
Oh, it was over here.
Yeah.
Oh, okay, good. We just put the wrong thing in over here for 3/4. Okay, good. All right. So it should be half here, and then these two were exactly here. So it should be 2 times 1. Okay, and then that would give us 5 over 6. Good. Much better. Thank you. And then we would get x equals 1/6 or 1/2 times 1/3. Excellent. And now we would get 1/2, 1/3. Okay, good. And let's think if this makes sense. So now we're saying the center of mass of these pieces has moved a little bit to the right. Before we had it was moving a little bit to the left when we had it as 2/3. And so the question was, does that make sense? Well, the first center of mass when we were doing this was at 3/4. And then the next center of mass, we had two calculations. One gave us 2/3, one gave us 5/6. What should be happening to the center of mass as we put more and more dominoes on? It should be moving towards the right. So is there any way 2/3 could have been correct? That means as we put more dominoes on, the center of mass is shifting to the left. Right? So from physical grounds, this should have been enough to scream at us that we had made an error. And I was actually a little bit concerned when I saw that because I could go from 3/4. It would be really nice if things kept moving in a nice pattern. And going from 3/4 to 2/3, if these numbers are going down, I can go to 1/2 next and then 0/2. This is dangerous. The pattern's not going well. But going from 3/4 to 5/6, I can see a good pattern coming from that. And your idea of saying, well, look, we know the piece has to be exactly here, put all the mass there, that's really good. And so now we will get 1/2, 1/3. And so now the overhang with 3 dominoes using this method is going to be 1/2 of the first, 1/2 plus 1/4, 1/2 plus 1/4 plus 1/6, and it's going to become the harmonic series. So at this point now, I feel comfortable with the induction that we say, yeah, the way you figure this out is you put all the masses of the previous ones right over here at the end point. And now we can go through and do the calculation. So let's see how much time is left. Okay, there's no time left, so we will stop the calculation there, and we will see that this is where the harmonic series comes into play. So good observation.